Hi, everyone. I hope you're doing well. Today, we're going to continue talking about scaling laws, and we're going to focus on transfer of heat. That is, scaling laws for heating up and cooling down. Now, this might be uh, take a little thought because it might be that the physics of heat is a little more unfamiliar to most of us than the physics of objects or forces, things we've talked about so far. But it shouldn't be too bad. Once we've got a handle on this, we'll use what we've learned to talk about something really interesting called thermal therapy. This is a medical treatment where magnetic nanoparticles are used to treat disease by heating them up. Well, you'll see what we're talking about in a minute. Here, let's go to the notebook and we can get started. Okay, so we'll talk about scaling laws for heating and cooling. And the first thing we want to do are to introduce and define some thermal variables. And these will be things like temperature and heat capacity and heat energy and heat flow. And well, you'll see what they are when we introduce them and define them, okay? And then we'll use what we have to show that the cooling rate of an object depends on its size. That is, there's a scaling law that tells us how fast a hot object will cool down. Okay? Kind of neat. After that, we're going to jump to an example called thermal therapy. And this involves heating tissue, so biological tissue, with magnetic nanoparticles. The magnetic nanoparticles will be excited with an electromagnetic field, oscillating electromagnetic field, and that's going to make them heat up. Okay. And in turn, that heats up the tissue inside of the patient. And if you have, if the nanoparticles are decorating a tumor or some diseased organ, then we can heat it up and destroy that tissue, hopefully without destroying everything else. Okay. And we'll see how the change in temperature that we can achieve scales with the size of the nanoparticles. Okay, which is something which is really interesting. All right, um, here, let's go to our definitions and get started. Some of these definitions will probably be very familiar to you. Maybe some will be unfamiliar, but probably worth going through them. The first thing, the first variable we want to concern ourselves with is the temperature. The temperature, when we describe it, will always be in Kelvin, or sometimes it's useful to work in degrees Celsius. And of course, these are related. 0 degrees, well, the temperature, as you probably remember, the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. Okay? Um, the second variable is the heat energy, which we'll call Q. Heat is a form of energy. And so when we want to describe the amount of energy that an object holds, heat energy that an object holds, we'll use Q. And Q has units of joules. I should say this notation isn't very widely used because it's kind of covering up an issue, which is that while heat is a type of energy, it's only one type of energy, and actually you can turn energy from one form into another. So normally it's not Q that's conserved, but total amount of energy. Anyway, that's not of any interest to us right now, so we'll just sweep that under the rug. And we'll call Q the amount of heat energy to help us keep track of that. Um, the next variable is the heat capacity. Okay? Heat capacity has units of joules per Kelvin, and it's defined in this way. The heat capacity of an object is given by the amount of heat we have to add to get a change in temperature, delta T. So, for example, if we find that we must add, let's say, 4 joules to an object to get the temperature to change by 2 Kelvin, then you can see that the heat capacity of that object, delta Q over delta T, would be 4 joules over 2 Kelvin. Well, it would be 2 joules per Kelvin. So that's heat capacity. All right? Big objects usually have big heat capacities, small objects, small heat capacities, but different materials behave differently too. Okay? In fact, that brings us to the next variable, which is the specific heat. This would be here, the specific heat per unit mass. So this would be joules per kilograms per Kelvin. Okay? And then there's a relationship between the specific heat and the heat capacity. The heat capacity is always equal to the specific heat per unit mass times the mass. You've probably seen heat capacity and specific heat before, and you might have seen other forms of specific heat, such as the specific heat per mole of substance, or the specific heat per cubic centimeter of substance. All right? But here we're using specific heat versus mass. Okay? And just for example, um, the specific heat of a particular substance, for example, for copper, the specific heat is 385 joules per kilogram per Kelvin. So for, let's say, a 250 gram copper block, the heat capacity of that object, that block, would be 0.25 kilograms times 385 joules per kilogram per Kelvin, or 96 joules per Kelvin. Okay? So, heat capacity and specific heat. Okay, I have one more. If we put a hot object in contact with a cold object, then heat will flow from the hot object to the cold object. And we'll call the heat flow P sub T. P for power and T for transfer, because it's power that's being transferred by heat flow. So this is the, hmm, 1 second, please. Having a little trouble with my pen. Okay, PT is heat flow and it has units of joules. All right? Here, let me illustrate what this means. So imagine we have a bar made out of some material, perhaps it's copper. And we arrange to heat one end of it perhaps with a heat source like a candle. And we arrange to cool the other end, perhaps by putting it in contact with some ice cubes. So that end is cold. All right. Then it turns out that heat flow will be equal to the following. It'll be um, a constant called the thermal conductivity times the cross-sectional area of our bar times the change in temperature over the change in position. Okay? This equation has a name. It's called Fick's law. And it describes heat flow. Notice the minus sign here. The minus sign makes it so that heat flows from the hot object towards the cold object, okay? Because if delta T over delta X is, if we're going from hot to cold, then delta T over delta X is negative, but the heat flow is positive. That's why we have the negative sign. And then, as I said, this term here is called the thermal conductivity. And it's different for different materials, of course. Typically high for metals and low for things like plastics or styrofoam, or I'm not sure. A is the cross-sectional area. Of our bar. And then delta T, delta X is the rate of change of temperature. That is, it tells us how fast the temperature is changing. So, for example, if the temperature changes by 1 degree over 1 meter, then of course delta T over delta X would be 1 degree per meter. Okay? All right. All right. I have one more result I want to share with you. Okay? This is a formula that expresses energy conservation. It's going to express the very obvious result that if heat flows out of an object, from a hot object to a cold object, and heat flows out of the object, then the amount of heat left in that object gets smaller. Okay? Here, I'm gonna let me make a drawing for this too. So now imagine two objects that are connected, say, by a little bridge, piece of material. And let's suppose, like the previous case, one of these is hot and the other one is cold. Then, from what we just learned before, heat will flow from the hot object to the cold object. And what that means is just this. If heat is flowing out of the hot object, then the amount of heat in the hot object must be declining with time. As energy flows out, the amount of energy that remains gets smaller with time. And so we can express it with this formula here, which says that delta Q over delta T is equal to minus PT. Okay? Okay, notice the units match on both sides. On the left side, we have delta Q in joules divided by delta T in seconds. So that's joules per second. And on the right-hand side, we have this power, which is also in joules. Oh my goodness, it's joules per second. not just joules. Okay? By the way, 1 joule per second is also called a watt, but we'll come back to that in a minute. All right, let's stop this video here. And then now, using what we have, these ingredients, we'll see how we can find the scaling law for cooling. There we go.